Okay, good afternoon, everybody. I'm Shuman Banerjee from the University of Wisconsin-Madison, and I'm very happy to bring you the final session of the day, which is on quality experiences. I realize we are between all of us and the boat, so we need to stick to time. Without further ado, I would like to introduce our first speaker for this session, Ehab Ghabashneh, who's a PhD student at Purdue in his final year, and he's worked on optimizing video delivery and analyzing data center traffic. He's looking for positions as a postdoc or in the industry, so let's welcome Ehab here.
Okay, thanks for the intro. Hi, everyone. Today, I'll walk you through our work called Dragonfly, Higher Perceptual Quality for Continuous 360-degree Video Playback. Now, this is a joint work between Purdue University and the University of Southern California. Well, now today, videos has a dominant share of internet traffic. And it's no surprise that this success in video has led to the advent of new forms of video, such as volumetric videos, AR, VR videos, and in the case of our talk today, 360 videos. Now, 360 is a bit different than the traditional form of video, which is the most popular form we have today, in the sense that users would passively consume the content of traditional video, while 360 has actually expanded the region of view to capture the full surrounding of the camera capture, allowing the user to explore different directions of their own choice and be more actively engaging with the content. Now, this brings an inevitable question. How should we stream 360 video to enable this immersive experience? Well, today there are currently mainly two ways to stream 360 video. The first one, which is the most common widely deployed in the industry, and that would be simply streaming the full 360 back to the user, irrespective of their motion. While simple, the main challenge here is that the 360 video can grow significantly in size. Without bandwidth requirement, that would far exceed the average US broadband bandwidth. Therefore, this traditional approach can't really support high-quality video experience. Now, for that reason, to overcome this challenge, recent work have actually proposed an alternative approach, which involves predicting the user motion and tell the transmission of the relevant regions of the video based on these predictions. Now, to achieve this, they had to introduce the video tiling process, which is simply you would take the full 360 video and spatially segment it into smaller regions. Then you would take each region and temporarily segment it into a couple of seconds of duration, which we refer to later as tiles. Now, although this method can significantly reduce the bandwidth requirement, but the issue there is that they still deal with 360 as a conventional ABR. In this sense, they try to optimize the quality and at the same time minimize and stall, and they would still stall if there's one single relevant tile is missing. And the problem here, and actually the stall in 360 video, comes from two conflicting root causes. The first one, which is motion misprediction. And there we find that the median accuracy for small look ahead of 3 seconds is only 25%. And it's not would only lead to rebuffering, but also it would be optimizing the quality of irrelevant tiles. And the other cause, which is pretty common in video, that would be mispredicting bandwidth. Now, rebuffering is an undesirable event for all sorts of videos, but it's bigger of a problem for 360. And this is because the user can still actually might move during the rebuffering, which would hurt their immersive experience. In fact, here's a snapshot from one of our user study sessions showing the user movement during rebuffering events. And there you can see the user can still make quite of a movement during the rebuffering, which could lead to cascading stalls, which would negatively impact the interactivity, which is the main objective of the full 360. Now, so far we've seen that tile-based rebuffering model obviously doesn't really support that interactive experience we're looking for. But this brings a question, can we stream actually 360 in a way without any stalls? Well, one thing you obviously can do is the naive skip model, and there you would be just simply skipping tiles that do not arrive on the time to keep track of the user motion, but doing so naively can lead to plenty of incomplete frames and missing tiles and poor perceptual quality, therefore it would be an acceptable user experience. So in this work instead, what we focus on is actually proactive skipping model, where we make a decision not to send fetch requests for some tiles if we believe this will improve the user experience. So for this work, we actually will demonstrate that proactive skipping would lead to better user experience than classical rebuffering model. And for that, we propose a new system called Dragonfly, which proactively skipping tiles for interactivity. So it ensures continuous playback without any stalls. And at the same time, it would be using utility-driven model in order to determine which tiles to fetch, which not to fetch, and those to be fetched in what quality and what order. So we evaluate Dragonfly with plenty of emulation and user study, and the results shows that we are actually outperforming the state-of-the-art Flare and Pano. So users in our study have actually rated 65% of Dragonfly sessions as good or excellent, while only 13 to 16% for Flare and Pano. And our emulation is showing that we are able to improve the median accuracy, the median PSNR by 1.25 to 2.8 x's without even stalling. But, so how exactly does actually proactive skipping work? Well, for that, let me just illustrate with an example. So let's assume that the user is currently missing a couple of tiles at the periphery, which are marked in red, and simultaneously is also missing critical tiles in the middle of the viewport for the next chunk duration. So there, instead of naively, you would be fetching the tile based on their deadline, although they may actually pass their rendering deadline, and at the same time would be cascading the arrival of the more critical tiles and prolonging the duration of incomplete viewport. What in fact we wanted to do is decide not to fetch these tiles at the periphery, instead just request these tiles, the more critical tiles, in order to be able to receive them by their time, which would lead to higher perceptual quality and interactive user experience. Now, how do we actually make that decision? Well, for there, let me just quickly go over the design key of Dragonfly, which is a utility-driven model. And there, first thing we do is we try to find whether the tile is relevant for each of the viewport or frame, for that matter, in our prediction window. Then we try to answer a couple of questions. So the first question we want to answer is how many frames would really benefit from fetching that tile, and also how critical that tile to each of these viewport. Is it going to be critically in the center, or is it more on the periphery side? And then, of course, we wanted to know what would be the value of the tile if it's going to be estimated to be arrived by time t. And we also look into another factor, which is the sensitivity of a tile to quality distortion. Now, here's a quick overview of the Dragonfly design, and you can see the primary stream there where we do most of the reactive skipping to enable interactive high quality experience. Also, we transmit a masking stream. Well, this is mainly just low quality to mask the missing tiles from the primary stream and further improve the user experience. Now, to evaluate Dragonfly, so you can see we did plenty of the emulation, relation study, and user study. But for the sake of time, I will only go over some of the results from our user study. Now, there we actually had, the participant had the ability to move freely, and the video will still reflect their own motion. And so there we had actually 26 participants. Each actually watched 5 videos, and that were streamed by 3 different schemes: Dragonfly, Flare, and Pano. And here you can find the distribution of the participants' opinion scores about all the sessions grouped by scheme, where 1 opinion score means poor experience, 5 being excellent experience. But looking into the percentage of sessions with 4 or more rating, we can find that majority of Dragonfly sessions actually had this rating, while only the minority of the state-of-the-art had the same rating. But we also dive deeper to understand the rationale behind this rating by summarizing the key observation from their qualitative feedback, which we collected during this study. Now, looking into the reactivity and quality feedback, we can see that the majority of users' reactivity feedback indicating Dragonfly being highly reactive, and at the same time, it's also managed to stream high-quality sessions. Now, to conclude, we just show that proactive skipping actually leads to better user experience than the classical rebuffering, which is what's followed by the current approaches. And for that, we propose Dragonfly, which is a system that's completely designed for proactive skipping in order to maintain interactivity. And briefly just show the results from our user study, where majority of users actually favored Dragonfly sessions, while only the minority of Flare and Pano. And the reactivity feedback indicating for most of the time we're being highly reactive while Flare and Pan are being slow to react. Last, we are also releasing the source code for Dragonfly and all other systems you can find in our evaluation, so please have a look at it. And that would be all from me. Thank you all. Happy to take your questions.
Thank you. So there's time for a few questions. Yep.
Hi, thank you for the talk. I just want to ask, Hunter from University of Chicago. Just want to ask, like, after you skip a frame, like, if this tile is needed later, do you just stream a completely new iframe, or like, do you just reference the previous frames? Like,
well, okay, so what we mainly do, we actually would determine to fetch a chunk. A chunk contains sets of frames, so it's not that we actually transmit in frames.
Okay, so like when you decide to skip, you're actually deciding to skip a whole chunk.
Yeah, if I'm gonna decide to skip, yeah, I'll probably just skip a chunk with a bunch of frames, right? But
got it.
Yeah.
So like, is it like after you skip a chunk, like then let's say like this part is like not being, like I'm not gonna be able to see this part for like a long time, right? If you're skipping like a whole chunk.
Right.
Got it.
Now, if the prediction changes, that utility-driven model will be able to capture now a different value of the tile and may be able to ask for it later.
Mm-hmm. But like then like it's a whole new chunk then, right?
It should be the same chunk. So what do you mean by a new chunk?
Because like I'm just thinking if the chunk is lost and like you need to retransmit it and the time has already passed, like you
No, we don't do that. So if the time is passed, it's passed.
Okay.
Yeah, I think let's take the rest of the discussion offline if that's okay. Any other short question? If not, let's thank the speaker again. Thank you. Okay, our next speaker is Pouya Hamadanian. And Pouya is a fifth-year PhD student from MIT and broadly works in automated decision-making, streaming applications, and ML inference. He's going to talk about cloud gaming media. So over to him.
Yep.
Switch.
Okay, thank you for the intro. Hi everyone, I'm Pouya and I'm here to talk about Ekho, or work on synchronizing cloud gaming media. In traditional cloud gaming, a VM in the cloud hosts the game engine code and rendering pipeline. This VM prepares a video and audio stream that we want to show to the player side. At the player side, we have a screen device that connects with a network path to the VM, and through streaming APIs such as WebRTC, it receives this video and audio to show to the player. Now there's a second device, an accessory device. It establishes a Bluetooth wireless connection to that screen, and using this screen as a proxy, it's going to send back input data to the server and receive any media relevant for playback at the accessory side. Now this extra hop adds 17 to 30 milliseconds of latency to the interactive gaming latency. It's not very desirable. So in modern cloud gaming, the architecture has shifted slightly. The accessory now connects directly to the VM, and it sends all the media that it needs to send back to the VM and receives all of it through that network link. Now you might have noticed that there's a synchronization problem here. At the screen side, we're trying to send game video and game audio, and at the accessory side, we're trying to send game audio, chat audio, and haptic feedback, such as controller vibrations. And we're trying to receive input data. These two sets of streams are over two different network paths, and because of that, they can be unsynchronized. The lack of synchrony here can ruin immersion. For example, if something happens in the game, and your controller vibrates in response to it 24 milliseconds before you hear the audio from the screen side, you're going to be able to notice it. If you look through all pairs of media, a max delay of 10 milliseconds is going to be enough for a seamless cloud gaming experience. So 10 milliseconds will be our goal. How do we achieve it? One simple approach is clock synchronization. If I could establish a link between the screen and the accessory, I could send timestamp packets between them and try a best effort at synchronizing their clocks. With a synchronized clock, I can synchronize their playbacks. Unfortunately, due to long distance and asymmetric paths, this delay estimation approach can have errors up to hundreds of milliseconds. Another problem is that the accessory and the screen device are not necessarily on a local network. While the accessory is always on Wi-Fi, the screen device can be on Wi-Fi, it can be on Ethernet, but very commonly it'll be on a cellular connection, such as when you're using a phone or a tablet device during traveling or commute. Finally, there are some delays that we cannot measure, and because of that, we cannot mitigate them using clock synchronization. So instead, we propose Ekho. Ekho is a robust end-to-end synchronization scheme. It works with a variety of network, it works in a variety of network situations with a variety of screen and accessory devices, and it's compatible with any streaming software that you design. To synchronize streams, all we have to do is find a pair of media among them and measure the delay between them. So we'll pick audio for now. When we send audio to the screen and the accessory, at the accessory side, we know when it's going to be played according to the reference clock that's the accessory's hardware clock. Now, we don't know when the screen side is going to be playing its audio according to that same reference clock. But fortunately, the screen and the accessory devices are in the same local vicinity. They're in the same physical location. So if the screen device plays its audio, we can pick it up at the accessory side through a microphone. And if we had a way of looking at that recording and saying, I can hear the screen audio at this specific time point, we could put two and two together and say that the delay is X. So how do we do that? How do we go from recording to finding where the screen audio is? A simple approach is, well, we know what game audio we sent to the screen, and we know what we recorded at the accessory. We can just directly cross-correlate these. And the time lag that gives you the max correlation is the delay that we're looking for. But this is a very rosy picture. In practice, you're going to have lots of distortions. Distortions such as background chatter, lossy compression that reduces the quality, and also the microphone connected to the accessory is not going to be studio-grade microphone. All of these distortions heavily affect the accuracy of this approach. Now, the main problem here is that the peaks in the cross-correlation plot are too short. And because of that, they can easily be sidelined by adding a bit of noise. The extreme ideal of what we want is a cross-correlation plot like this, where at the correct time lag, there's a strong correlation, a very sharp peak, and everywhere else, it's near zero. And ideally, if we add any noise to this to the recording, we would, the peak wouldn't get sidelined by the noise. Now, we cannot, although this is the ideal, we cannot achieve it with just cross-correlating game audio. So we leverage an old technique that's used in a variety of domains, such as time recovery and GPS. We employ markers. In our case, pseudo-noise signals, such as white noise, that have a very nice-looking autocorrelation plot. There's a very sharp peak that's going to help us immensely when we want to detect that marker. But the noisy nature of the signal itself, which is essentially white noise, is going to be making it very easy to mask it. And I'll soon explain why that's important. So how Ekho works is before I send the game audio to the screen side, I'm going to embed these hidden markers inside of that screen audio. When I get the recording from the accessory, I'm going to now cross-correlate it to the marker directly. And the resulting signal has extremely sharp peaks. Each one of those peaks is a marker. Now, critically, we have a standardized crowdsourced experiment that shows users cannot hear these markers. We've hidden them well. And the exciting thing is, even though I talked about trying to synchronize the delay between two pairs of audio, this approach works even when you mute the game audio from the screen side, and I'll circle back to that towards the end of my slides. There's a few extra pieces in the signal processing pipeline. I won't have time to talk about all of them. But what I do want to highlight is that Ekho is backed by an analytical model that lets you measure its confidence in each peak it detects. And that's why Ekho is robust to each distortion that we talked about. Okay, having figured out the synchronization delay, how do I compensate for it? One simple approach that we do here is I could pause the faster side to let the slower side catch up. We can do this pausing by adding empty silence packets. That's one approach. Another approach is I could skip audio packets in the slower route. For example, in the top right, you can see the screen audio wants to play audio packet number 12 next, but I'm going to have it skip to number 13 so that it also catches up to the accessory side, which also wants to play audio packet number 13. Now, by default, we're going to use the silence approach. But whenever we can, we're going to be skipping packets, because skipping packets doesn't increase end-to-end latency. Let's see how Ekho works end-to-end. At the top left, you can see the screen video, and you can see visualizations of the audio signals. You'll soon be hearing them as well. You can see the visualization that these two audio signals are a little bit apart. At this point, we activate Ekho.
At least we're all together.
After about 3 seconds, Ekho detects that there's an 80 millisecond latency between these two streams. And it fixes it by adding 80 milliseconds of silence into the faster route. Now, if you listen to it, you're only going to hear a single source.
Me, Rose. Now, everything's going to be...
All right. Now, for a real-world experiment, we're going to replace the accessory on the screen side with 2 laptops. We're going to connect the accessory side through campus Wi-Fi, and we're going to connect the screen side through cellular network. For the server, we're going to be using AWS C4 instances in the East 1 and 2 regions, and the streams are both on either side going through ORTC. The microphone that's connected to the accessory is an on-device microphone of the Xbox stereo headset. We repeat this experiment for 3 sessions. Each session is 5 minutes. And here, I'm showing you the distribution of the delay when you don't have Ekho active for that entire 15 minutes. The delay here is at least 50 milliseconds at all times. When we activate Ekho, however, we can see that it achieves its 10 millisecond synchronization goal 87% of the time. Ekho is by design resilient. If we experiment without adding any background chatter, Ekho, out of all the markers that we've added, is able to measure 100% of them across the entire gaming library. Compared to prior work that uses direct cross-correlation, they cannot detect any delay in 37% of the gaming library. If we add background chatter, however, Ekho degrades a little bit. It's now able to detect half the markers in a small subset of the games. But prior work fails to detect any delay in 80% of the gaming library. Now, let's circle back to that. Finally, let's circle back to that scenario that we talked about. What if we want to mute the game audio from the screen side? Well, in this case, we can still let the marker play, but we're going to mute the game audio at a software level. We have to be careful about the marker amplitude here. I'm showing you the screen audio volume as a measure of that marker amplitude. And you can see that up to 18 decibels, it's quieter than what you expect from a quiet library. From a detection standpoint, Ekho can detect 100% of the markers for any amplitude 12 decibels and above. So any amplitude 12 decibels to 18 decibels should be fine. Now, what if I told you that throughout this talk, from the very first slide, I've been playing that marker? If you didn't hear it, or if it didn't bother you, you're going to have a fantastic experience with Ekho. To conclude, Ekho is the first robust and universal end-to-end synchronization scheme. And key to Ekho's design is the use of pseudo-noise markers that act as a sort of timekeeper across devices. That marks the end of my slides. Thank you for your attention.
Thank you. So time for a couple of short questions. So you use a microphone.
Danny Chen from Princeton, a very great talk. So early in the talk, you mentioned that accessory may connect to the screen directly using something like Bluetooth. So have you compared the accuracy for using Bluetooth versus using sound?
The reason that people don't use Bluetooth anymore, at least in Amazon Luna and Google Stadia before it shut down, is because it increases the interactive gaming latency. It's not at all about synchronization. It's that when I press a button, now it takes 17 to 30 milliseconds more till I hear it.
But I mean, you could still send the button to the cloud, but you can use the Bluetooth channel just for cloud synchronization, right? Oh,
well, there are some problems there. The accessory device, for example, cannot be connected over the wireless and Bluetooth at the same time. And there was also some considerations that we had to take because some screen devices don't have Bluetooth enabled.
Got it. So also one last question, have you compared the power consumption for running algorithm on the headset versus, let's say, using Bluetooth to do the synchronization?
Not really. So Ekho doesn't actually increase any power consumption on the accessory side because the accessory side already collects a recording and sends it back to the server because of chat audio that's sent back to the server. So we're only taking that chat audio at the server and we're doing some signal processing with it. So Ekho doesn't actually add any power.
I see, so on the server side. Okay. Thank you very much.
Sure.
Okay, one more question.
Hi, great talk. So it's impossible.
Could you introduce yourself, please?
Oh, sorry. I'm Santosh from Texas A&M University. like you mentioned, it's impossible to synchronize two clocks if the delays are asymmetric. All right. So could you please explain like how this approach makes the delay symmetric to reduce the accuracy of delay estimations? Thank you.
Sure. Yeah. So what we're doing here is we're measuring the delay between what the accessory is playing and what the accessory is hearing. It's completely end-to-end, so there's no networks involved here. We're directly saying the two signals that on either side of the accessory, I want to minimize the delay between them. So it takes everything into account. Even how long it takes for the audio wave to travel from the screen audio, the screen device to your ear, which is non-trivial in this case.
Let's thank the speaker once again. Let's have the next speaker come up. You have to switch your laptops, right? Okay, maybe let's get that going. Yes, please. Where is your laptop? Oh,
Where was the laptop? It's here.
did somebody walk away with a laptop?
I can bring mine if that works.
Yeah, why don't we? Oh, thank you.
That's why we don't.
Okay, while that's getting set up, I will briefly introduce the next speaker. So our next speaker is Prateesh Goyal from Microsoft. He's a senior researcher there in the networking research group, and he wants to let you know that they are hiring both interns and full-time people. So he invites you to visit the Microsoft booth during lunch, and he's going to talk about stock exchange or financial exchanges and fairness in those settings.
Yes.
So take it away.
Thanks, Suman. Hello everyone. I'm Prateesh. Today I'll talk about cloud-hosted financial exchanges. I'll present DBO, which is a simple mechanism that ensures fairness among competing traders in cloud environments. So recently, there has been a lot of interest to move financial exchanges from on-premise to the cloud. Several exchanges and cloud providers have announced business partnerships to this end. There are several reasons for this interest, for example, ease of management. Now, before any exchange can move to the cloud, there are a few technological barriers that need to be overcome. One such fundamental barrier is fairness. To understand why, let's see how an exchange works. In an exchange, the central exchange server produces market data continuously and sends it out to various market participants. The participants use this data to generate trades. These trades are ordered by the exchange server in a first-in, first-out manner. Now, critical clientele for exchanges is high-frequency traders such as Citadel. These traders are engaged in speed races where they're competing for the same trading opportunity. There's an arms race in these high-frequency traders to respond to the market data the fastest and win the speed race. In these settings, even minor disadvantages in networking latency can change the outcome of a speed race and kill competition completely. To enable fairness, exchanges today have over-engineered their on-premise networks to provide equal bidirectional latency. This way, the market data is delivered simultaneously to all the participants, and the trades are processed by this exchange server in the order that they are generated. These two properties together ensure fair competition. As I mentioned earlier, moving to the cloud is very challenging. In particular, unlike on-prem data center networks, it's very hard to ensure equal latency in the cloud. Now, there are many reasons for this. For example, the wireless of the cables might differ, there might be congestion in the network or delays at the end host. As a result, it is very difficult to ensure simultaneous delivery of market data in such environments. Recently, there's a proposal called CloudX, which proposes using clock synchronization to achieve simultaneous delivery of data in the cloud. The solution works as follows. Corresponding to each participant, there's a co-located release buffer. These release buffers are clock synchronized and responsible for releasing the market data simultaneously. In particular, market data generated at a particular time is released by these release buffers at a later pre-specified threshold. For incoming trades, the release buffer also marks a timestamp corresponding to the time the trade was generated. The ordering buffer then orders these trades based on this generation time before forwarding them to the exchange. This way, CloudX aims to facilitate fair competition. There are two fundamental problems in using clock synchronization to solve this problem. The first one is already known, that it is very hard to achieve perfect clock synchronization. The second one is that even with perfectly synchronized clocks, it's hard to ensure simultaneous delivery of data. When network latency spikes above the latency threshold, such solution incurs unfairness. In the paper, we actually show that simultaneous delivery of data is impossible in cloud environments with unbounded latency. This result is a simple consequence of the classical two generals problem. So, given these challenges, what do we do? One solution is that to achieve simultaneous delivery of data, we can re-architect our clouds to provide both perfect clock synchronization and bounded latency. In this talk, we will not re-architect the cloud. Our solution, delivery-based ordering or DBO, takes a fundamentally different approach to achieve fairness in the existing cloud. In DBO, we don't try to achieve simultaneous delivery. Instead, we achieve fairness by correcting for latency differences in delivery of market data. This post-hoc correction approach has some really nice advantages. In particular, DBO provides guaranteed fairness for speed racing in existing uncertain cloud networks without requiring any clock synchronization or bounded latency. Further, DBO provides fairness at low overall end-to-end latency. To understand how we correct for latency differences, let's see how a speed race works. In a speed race, multiple participants are competing for the same trading opportunity. A particular market data point serves as a trigger for the speed race. The outcome of the race is simply determined by the order in which trades are processed at the exchange server. The figure here shows an example of a speed race that is triggered by data point X. The figure also shows the response time, that is the time it took the participant to respond to the trigger. Now, since outcomes of a speed race are determined by the order in which trades are processed, to achieve fairness, here all we need to do is order competing trades based on the response time. So in this example, all we really need to do is order trade from participant 2 ahead of trade from participant 1. We refer to this particular kind of fairness as response time fairness. It turns out that it's also impossible to achieve response time fairness in network environments with unbounded latency. This theorem is a consequence of the fact that the trigger point of a trade is unknown and the classical two generals problem. What DBO guarantees is a slightly weaker version of fairness called limited horizon response time fairness, or LRTF. As per LRTF, only trades with response time lower than a certain threshold are ordered fairly according to the response times. LRTF is still a useful guarantee, as most high-frequency traders typically respond very fast within microseconds. I will now give a high-level overview of DBO. Our core approach is inspired by the use of logical clocks in distributed systems to order events in uncertain network environments. DBO introduces a new kind of logical clock called delivery clock to order trades fairly. The overall architecture of the solution is similar to that of CloudX. In DBO, each release buffer maintains a separate delivery clock. The release buffer marks incoming trades with the delivery clock timestamp at their generation time. The trades are then ordered at the ordering buffer based on this delivery clock timestamp instead. At a very high level, delivery clocks track time relative to the delivery of market data at the participant. Formally, delivery clock is a lexicographical tuple where the first element corresponds to the last data point delivered to the participant. The second entry measures the time elapsed since the delivery of the last market data point. I will now show you how delivery clocks can help correct for latency differences in delivery of market data. So consider this simple speed race triggered by data point X. In this example, delivery clock of participant 1 will read the following at the time of trade generation. Similarly, delivery clock of participant 2 will read the following. Now, since response time of trade from participant 2 is lower, the delivery clock of participant 2 will be lower than delivery clock of participant 1, and trade from participant 2 will be correctly ordered ahead. This way, the delivery clock is able to correct for latency differences and order trades fairly. Here, one thing to note is that delivery clock corrects for latency differences using the last data point. Now, if the last data point and the trigger point are different, then the latency correction might be inaccurate. In DBO, the exchange server batches data and the release buffer paces the delivery of this data. With batching and pacing together, DBO provides guaranteed LRTF. For details, please see the paper. We did a cloud-based evaluation of DBO. The table here shows the latency numbers for DBO. It also shows what fraction of trades were ordered fairly. The table also includes results for direct delivery where there is no ordering or release buffer. As expected, direct delivery achieves poor fairness because of variations in networking delay across participants. In contrast, DBO achieves 100% fairness. In this table, we also report max RTT across all participants. In the paper, we show that this max RTT is the minimum latency required to achieve fairness. DBO's latency is actually close to this bound with additional delay due to batching and pacing. In this experiment, overall, DBO provides perfect fairness at sub-100 microsecond cloud latency. To compare against CloudX, we use simulations. The figure here reports the fairness and average latency numbers. For CloudX, we report results across different latency thresholds. Overall, DBO achieves perfect fairness at much lower latency. To recap, I presented DBO, the first mechanism that enables guaranteed fair speed racing in uncertain network conditions. Our evaluation shows that DBO can achieve sub-100 microsecond latency in the cloud. Under the hood, DBO uses logical delivery clocks to correct for latency differences in delivery of data. Finally, our approach is general and might be suitable for providing fairness in other settings such as online gaming. With this, I'll stop. Thank you.
Thank you. Time for a few questions. Yeah.
Hi, this is Wei Tao from Rice.
Could you introduce yourself? Introduce yourself.
Yeah, this is Wei Tao from Rice.
Oh, sorry, I couldn't hear.
Yeah. So I have a question about the DBO, which is if one message contains multiple packets, do we take the first packet as DBO or the last packet as DBO?
If one message contains multiple packets?
Multiple packets, yeah. And on one host, it may receive like 10 packets within 10 nanoseconds. In another host, we receive 10 packets within 15 nanoseconds. So we take the first packet as DBO or the last packet as DBO.
Oh, like you mean within a batch?
Yeah.
I see. Yeah, so I think if multiple packets of a batch are not delivered simultaneously,
yeah,
there might be some more unfairness introduced. We actually quantify that unfairness in the paper, but I think typically we expect that a single jumbo packet or something will be able to deliver the entire data within a batch.
Oh, you mean single jumbo packets? I see. Okay.
Yeah.
I had a brief question, which is, can you give us a sense of the worst case sort of delays that might be incurred to accomplish fairness under different network conditions? Is there some guarantees you can?
So, like, if you really think about it, like, the minimum latency that is required to achieve fairness is maximum RTT across all the participants. So the solution has two components, which is like first is like using delivery clocks and ordering trades with delivery clocks. So the latency of that solution is very close to the maximum RTT. And when we do batching and pacing, we do batching and pacing because we want hardcore guarantees. But just using delivery clocks alone provide for latency correction, but the latency correction might be incorrect. With batching and pacing, you introduce additional delay, which is proportional to this delta parameter that I was talking about.
Thank you.
I have a question.
Yeah, okay.
I'm Tom from Columbia. Cool talk. It looks like you're measuring latency on the trader side?
Yeah.
So does this introduce trust issues that wouldn't be there in the classic on-prem setting?
Yeah, so the release buffer component that is kind of maintaining the delivery clock, it has to be under a trusted domain. So we kind of imagine that there are multiple ways it could be implemented in the cloud. It could be in the virtual, it could be in the virtual NIC, it could be in the hypervisor, but wherever it is, it has to be under our, like the cloud provider's control. Yeah.
One last, keep it short.
Hi, Andy Myers from Jane Street. How do you handle multiple market data sources from different publishers?
I see. So we kind of imagine like multiple things. So one could be that if you have, say, some sort of external data, you could try and serialize it with the existing market data stream and kind of ensure fairness with respect to such a super stream. I think the overall latency with DB, at least in cloud, that we are seeing is still like under 100 microseconds. And the external data which comes in has a latency of order of milliseconds, right? Because it's maybe like news which is flowing across the US or something like that. So we also envision that maybe it might be just okay to not like try and synchronize, not try and sort of serialize the external data stream with the market data stream, and the unfairness introduced might not be much.
Thank you again. So our final speaker for this session and the day is Frank Sifei Luan, who's a PhD student at Berkeley and works with his advisor, Jon Stryka, and his research interests in AI systems. If you can come up and get set up. And he's going to talk about an extensible shuffle architecture. Just get out of this one. Can I just start this? Hello?
Hello, everyone, and thank you for staying until the last session, last talk of the day. My name is Frank. I'm a PhD student at UC Berkeley, and today I'm excited to talk to you about Exoshuffle, an extensible shuffle architecture. This is work with my fellow colleagues at Berkeley and at AnyScale, yeah, let's jump into it. So shuffle, we're talking about shuffle here in the context of distributed data processing. So shuffle happens whenever there's an all-to-all data communication between all nodes in the cluster. For example, if you take a look at MapReduce, this is a classic MapReduce paradigm. Shuffle happens whenever there's a map stage and there's a reduce stage, and then all of the mappers need to send data, each of the mappers needs to send data to one of the reducer tasks. So this creates the all-to-all communication pattern. This is the most expensive data communication in distributed data processing. It is also ubiquitous. So in modern day frameworks, so data frameworks, things like Spark, Presto, and older frameworks like Hadoop, people usually write these high-level SQL operations, and a lot of them actually translate into these shuffle operation down the hood. So things like, think about selecting distinct elements from a large data set, sorting, grouping by, and some joins, such as sort merge join, all of them would involve shuffle execution under the hood. And framework developers have often need to re-implement shuffle from time to time. Here are some reports from industry. So LinkedIn reports that there are petabytes of data being shuffled every day. Facebook reports there are tens of terabytes of data, and then more than half of their Spark jobs involve at least one shuffle operation. So what is challenging about shuffle? So the challenge comes from the fact that if you have n nodes in your cluster, then shuffle is an n squared operation. So if you have, essentially translates into moving a very large number of very small blocks across the network. So let's take an example. So you have a terabyte of data to shuffle, to process, and then you have the 10,000 partitions. So this easily translates into 100 million shuffle blocks, each of only 10 kilobytes. So think about moving these blocks through network, disk, and memory boundaries. So this makes it difficult to optimize for a few reasons. First, this creates challenges for I/O efficiency. It's inefficient to just send these blocks without optimization. Fault tolerance becomes important because if one of these blocks fail to transfer, the system must be able to handle them transparently. And finally, if the data is skewed, then there's a problem of load balancing. So the traditional solution to this shuffle problem is that people build these what we call monolithic shuffle systems. So these are basically distributed systems that whose entire purpose is to support shuffle in data frameworks, and then they're usually deployed alongside data processing frameworks. So a lot of them have been built from the open source industry, from industry, and from recently cloud providers. Each of these are targeted at a specific use case. So things like for hard drive clusters, for SSDs, for disaggregated storage, where the storage is separated from the compute, and more recently for cloud storage. So I guess one question is, why are people keep rebuilding these shuffle systems? And that they are costly to develop. So let's think a little bit about what is inside these shuffle systems and how they optimize the shuffle operation. So they are usually built as one big system, and then there are usually two aspects to the optimization. One is we call the control plane optimization, which is basically about when and where to schedule the task, and when to move the blocks and how to merge the blocks after transmit. The other one is about the low-level optimizations to efficiently transfer blocks and things like that. So they're usually built as like one big box of the system, and then they're deployed to support a data processing framework on top. So this creates two problems. One is that the control plane and data plane are tightly coupled, and the result of that is that if you want to sort of invent a new shuffle optimization or different shuffle strategy, you basically have to rebuild a new shuffle system to do it. The other one is that these systems are built to support more of the traditional BSP-style systems like synchronous processing. So it makes it difficult to interoperate with new applications which require more fine-grained pipelining. So one of such example is distributed machine learning training. So the problem is like this. So you have a big data set that's somewhere on the cloud. You want to use that to train your machine learning model. You're going to use several GPUs to do it. Now, you want to randomly shuffle these data before feeding them to your GPU because this eliminates bias in the training data. So ideally, what you want is you want to kind of stream the shuffle results into the GPU while the shuffle is happening. But this is difficult to do, for example, with Spark, because Spark provides one synchronous interface that you can only consume the shuffle result after they're being shuffled. And it's not so easy to adapt to this existing system because of the tight coupling that we talked about before. So in this paper, we present Exoshuffle and an extensible shuffle architecture. So how this works is that we build shuffle on top of a common general purpose data plane. Here we use Ray. It's a distributed execution framework for general Python applications. And then with a programming abstraction we call distributed futures, we can actually decouple the control and the data plane of shuffle and just be able to express shuffle, these different shuffle strategies as application level libraries. So things like pre-shuffle merge, so these are the optimization in previous literature to optimize for shuffle. These can be implemented just as regular Python programs. And then with that, it becomes much easier. And with the distributed futures references, it becomes much easier to interoperate with applications which including data processing, but also include other ones such as distributed machine learning training. So here we decouple the control plane from the data plane by using an abstraction we call distributed futures, and then we're able to improve the interoperability between shuffle and other applications. So we will show that in the control plane, this makes it much easier to implement new shuffle algorithms, and this makes it much more flexible to interoperate with other applications. On the data plane side, we're going to show that this decoupled architecture actually can provide the same performance and scalability that is competitive with monolithic shuffle systems. Now let's take a minute to talk about the distributed futures API. So a distributed future is essentially, think of it as a reference that is pointing to some value in a distributed cluster. So it can be on a remote node, and it can be a future value. So these two lines of code here is actually enough to express this all-to-all data communication pattern. So here we call, so this dot remote annotations will basically turn functions into remote tasks, and then they will immediately return and then give you a list of references that can be used to pass to other tasks. So for example, here we pass from each of the map output, we pass one reference to the reduce task. So this essentially creates that shuffle pattern. And then we don't have time to look at more code, but believe me that this is actually pretty easy to implement these more complex communication patterns that are used to optimize for shuffle. So the decoupling happens because now the application only needs to specify a few things. It only needs to specify the task graph, as we have seen. And then optionally, it can provide hints like when to run task and then where to run task. On the other hand, this general purpose data plane can provide a lot more system functionalities, such as resource allocation. It provides memory management. Most importantly, it provides the ability to transfer objects between nodes. It can handle automatically spilling objects to disk and recovering them from disk. It can handle garbage collection when the references go out of scope. And it can implement things like pipeline I/O, which overlap I/O and execution, and finally, fault tolerance. We want to know that all of these functionalities are should be applicable to a wide range of general applications and not just specific to shuffle. So with this, let me run through the evaluation in 2 minutes. So we want to answer a few questions. First, does the Exoshuffle architecture make it easier to implement shuffle optimizations? For this, we implemented a few common shuffle optimization in previous systems, and then we show that basically we can write the same application, write the same algorithm, and get the same performance, but with 10 to 20x lines of code. Second question, does Exoshuffle provide the performance and scalability that is competitive with monolithic shuffle systems? For this, we run the TerraSort benchmark, which is basically sorting a huge amount of data. We run it actually on 100 terabyte of data. We run it on a cluster of 100 machines, and then we compare with Spark. The TLDR here is that we are able to scale to 100 terabyte of data on 100 nodes, and then we can actually exceed the performance of Spark. We also run the CloudSort benchmark. So this is a benchmark about what is the cheapest way to sort 100 terabyte of data on public cloud. What is the cheapest way to do it? We're able to beat the previous state-of-the-art by 37% by being able to to sort 100 terabyte of data with less than $1 per terabyte. Finally, for the machine learning example that we're talking about, we show that with Exoshuffle integrated with PyTorch, we can achieve, first of all, faster training throughput, so that's the shorter line, and also a higher training accuracy, that is the higher line. So in summary, we show Exoshuffle and Extensible shuffle architecture can reach the performance and scalability of monolithic shuffle systems, and that by decoupling the control and data planes, Exoshuffle can benefit a variety of applications by providing efficient shuffle. Thank you all for listening, and happy to take questions.
Thank you. So time for a couple of questions. Yes.
Hi, this is Jashin Ling from UT Austin. Thank you for the talk. I'm wondering, like the Exoshuffle can be only used to the batch analytic job, or it can be adapted to other like stream analytic or other kinds of job? Yeah.
Yes, good question. So yeah, the point of building Exoshuffle is to make it available to not only just batch processing, but also stream processing and these more fine-grained applications such as machine learning training, which is essentially pipeline shuffle.
Okay.
Okay. I think let's thank the speaker again and then bring all the speakers to stage. Okay, so maybe I could start by seeing if any of you want to ask each other a question. Great.
So I would like to ask if DBO can be used actually to solve, through the fairness of latency, can be actually solve the synchronization problem with the audio from Ekho.
Yeah, good one.
Yeah, we've actually had that conversation before. From my understanding, DBO achieves a clock synchronization by building a sandbox world, where each specific device, each specific node is in a sandbox, but it's going to see those messages in the same timing order. That doesn't mean in the real world they're going through those messages at the same time. It just means that in the sandbox they're going through them in the same time. We can't use that for cloud gaming because we are in the real world there. Is that right, Prateesh? Want to comment on that?
And maybe the reverse question is also valid.
So I think we were talking about a different project. That this is not DBO. Yeah. But yeah, I don't think like the two projects are related in any way. We are not trying to do synchronization in any way, trying to synchronize like two different streams. What we are doing is like, hey, you have the same thing and it's not delivered simultaneously. Can you correct for differences? They actually want to deliver the thing simultaneously. Yeah. And because the two things are in same proximity or physically they're in the same thing, it's still possible to do using like the technique. Yeah.
Anybody else has questions? I had a high-level question about generally about user experience and quality. You know, we often have bandwidth or throughput, and we have latency, and most of the recent work that you're talking about is focusing on latency. How does availability of bandwidth factor into many of these applications at this point? I mean, I know that in your 360 VR that has a big role, but what about gaming and so on? How do you see if the trade-offs have to be made to optimize for one or the other? How do you think about it? Maybe it doesn't apply as much to Exoshuffle, but maybe the other three, if you have any comments.
I know from past work in cloud gaming, like in cloud gaming itself, not in synchronizing cloud gaming media, that you can trade off compute and bandwidth to get less latency than one RTT. It is possible. It's just exponential. That's the only thing that I really know of, if it helps.
Okay.
Yeah, I mean, for video latency, I mean, yeah, so bandwidth would completely change how the algorithm would work, what it would really get, but latency is less critical in videos. But yeah, bandwidth will change the whole, optimize it. I mean, the result of the optimization will be completely changed by that.
I think maybe we can try and like find fundamental trade-offs in every possible space, and maybe as soon as we hit the boundary, we think about changing the underlying stuff. If your congestion control is not able to achieve more bandwidth or like lower latency, you need better links. Eventually, like the underlying hardware has to change, or like the underlying network has to change at some point in time.
Got it. Anybody? Okay, there's a question from there. Go ahead.
Hi, I'm Santosh from Texas A&M. It's basically a very high-level questions to Goyal and for the author of Ekho. So it seems like the clock synchronization is kind of a bottleneck for a lot of applications, like what Goyal also pointed. And do you think there is an opportunity for like next generation of routers that try to stabilize or at least forward the delays what they experience in the intermediate paths, or some sort of establishing delay symmetry in the network path would help solve some of these issues?
So just to clarify, I think like in that particular problem, just solving clock just having perfectly synchronized clocks is not enough. But in general, like whatever you do, you want to use wireless, you want to use intermediate routers to give more information for like better synchronized clocks. It should help, and it's also a real problem. There are like real companies, real startups, which have raised like millions of dollars, like trying to do this. So, yeah.
As for synchronization, if there is some infrastructure for synchronizing clocks, why not just use that instead of Ekho? But I think the clock synchronization problem is more complex than the problem that I was covering. So yeah, trade-offs. Make your own choice. Okay. Regarding to symmetry, I'm not an expert in it, but from what I know, sometimes some providers deliberately make their paths asymmetric. They take their service paths from some specific set of routers, and the reverse path is something else. They do it by design. So I don't think it's going to go away.
Thank you so much.
Okay. We have one more question here. We're waiting for a quick run of the microphone. There you go. Latency is being reduced here. Thank you.
So one of the infrastructure for synchronization is GPS, right? Google used GPS to synchronize banners. So I just wonder, why people didn't adopt this kind of radio-based, naive physical synchronization, both for trading and both for gaming. We just use a single radio signal to synchronize both devices. Is that because cost or what reasons? I'm Danny Chen from Princeton University. Sorry, I forgot.
So I think in my case, it's very simple. You just can't have a really big antenna connected to your accessory, and it's too costly. I'm going to let Prateesh answer the other one.
Yeah, probably clock synchronization can help. Yeah, we don't. I don't think. Maybe it's costly as Yana is saying. I don't. There might be legacy reasons as well. You might have deployed a huge part of infrastructure which doesn't have this thing. Now you have really good synchronized clocks on half of your infrastructure. How do you work with the remainder one?
But most gadgets have GPS these days, right?
Well, sorry? But what kind of accuracy are we really talking about, right? So I think some of the papers actually do talk about I'm misremembering, but they also use GPS pathways as a fallback thing. But even then, I think the accuracy is still limited. Yeah.
I don't know if game controllers have GPS in them, but maybe they do. I don't think so. But anyways, I think that was very interesting. Any other questions? And if not, the general chair is here pointing stuff at me. Yeah, I know. So then that brings us to the end of the session here today. Thank you.